Very beginning of this lesson, I talked about aspect ratios, widescreen being 16 by 9, which we're all pretty much familiar with, but the old version of a television in 4 by 3, and there was like this problem. Okay, I've got this television, which is in 4 by 3, and then I've got this CinemaScope, really super wide movie. How am I supposed to display this image on my television? Right, and this is what companies came up with that put out things like DVDs, and at this point, I guess it was VHS, if you've ever seen one of those things. So when buying a copy of a film, prior to the adoption of this 16 by 9 widescreen standard, consumers had to make a choice between a pan and scan truncated version of their picture and a what was called the letterbox shrunken down image to fit on their particular screen. If you look at the animated picture up there at the top, they would have this widescreen version of the film, and it was too big, it was too wide to fit on the screen. So they're going to cut out this smaller rectangle, and you can see this rectangle moving around the picture, and this is what was called pan and scan. The image was still, but they would move around the part that they would keep on that image in that little rectangle. Lots of extra movement that wasn't originally in the shot, and then also you'd leave out a lot of information. Speaking of leaving out a lot of information, if you look at the Star Wars pictures that are right down below, each one on the left-hand side was the full screen version, the pan and scan version over here, right? Compared to the letterbox version where you're seeing the full image that George Lucas intended. So what's really, really terrible is if you look at this bottom one here, you see Luke Skywalker, but you don't even see the fact that Obi-Wan and Han Solo is in the picture. They just completely get cut out. All right, so in about 1984, this guy came along. His name was Kerns Powers, and he came up with a compromise, something that would basically a screen size that would preserve both of these images, a 4 by 3, which is what televisions were broadcast in, and then even the widest of movies, it would still fit in the same picture, and the picture would have the same area. So remember, if I come back over here, one of the reasons why people didn't like Letterbox is because it shrunk down the image to fit on their screen, putting black rectangles up at the top and the bottom. It was too small, okay? So Dr. Powers came up with this new aspect ratio that was a compromise between two of them so that this 4 by 3 rectangle that we see here has the exact same area as the CinemaScope, the 2.35 to 1 rectangle here, right? So let's see the mathematics involved in coming up with this aspect ratio. And I'll hope to tie it all into this idea of geometric mean, which is pretty much what the lesson was supposed to be about. All right, so his name was Kerns Powers, came up with this 16 by 9 aspect ratio. So the main idea is I want to take the 4 by 3 picture. Let me draw ourselves a rectangle for this 4 by 3. And this longer leg down here is going to be a 4, and the shorter one's a 3. But that's what it would reduce to. Now, what I would do is I'd probably scale this up by some sort of scale factor, and I'll call that scale factor an A, right? So if I were to just take the ratio of those two sides, I'd have, I'd say 4A over 3A, and your 3's would cancel, and you'd have your aspect ratio of 4/3. All right, awesome, perfect, okay. All right, now, I'm going to say its area is A. So let's find the area of this rectangle. It's very easy. It's just the length times the width here. So the area is going to be a 4A times a 3A. Area is equal to 12A squared. All right, and now what I'm going to do is I'm just going to solve that for A, this scale factor here, okay? So I would divide over the 12 and then take the square root. So I'd have A over 12 is equal to A squared, which means that A is equal to the square root of little a is equal to the square root of big A, which is the area, over 12. All right, nice. Let's do the same thing with that widescreen aspect ratio. I think I'll do this one in green. Okay, so super wide screen. Now, on this one, we would have 2.35 to 1. Except for this 2.35, I don't want to have to deal with all of these decimals inside of the fractions, so 2.35 is the same thing as, go over here to the calculator and you will see, it is 47 divided by 20. Try that again, 47 divided by 20, put a decimal place at it. There you go. So 47 to 20 as a fraction. So I'm going to make this thing 47 and this one 20. Okay, and then I'm going to have to scale this thing up because I can probably bet that they're not 47 inches by 20 inches or centimeters or something like that. And I'll call the scale factor B in this case. Okay, and when I find its area, this area needs to be exactly the same size as this area because I want them to have the same area whenever I display them on the screen, this new aspect ratio screen. Okay, so in this case, our area should be 20b times 47b. So our a squared, not a squared, what the heck? A is equal to 20 times 47 is 940. B squared. All right, and I'm going to do exactly what I did on the purple side over here. I'm going to solve that for B, so I'll divide over our 940. And then take the square root, so B is equal to the square root of A over 940. All right, so far? Excellent. Okay, so then I'm going to draw in our new shape, our new rectangle. I don't want purple because that other one's purple. So let's come back up here to this picture. And now notice that our 4x3 rectangle has the height of our 16 by 9 widescreen, okay? And then our CinemaScope one is the one that has the length of our 16 by 9 down here, okay? So I'm going to redraw our new rectangle. This is going to be our 16 by 9, but we don't know it's 16 by 9 yet. We're trying to come up with that. So its area is not going to be the same as these two areas, right? If I look at this image, you can see that it has extra bits on each one of these quarters. So the area is not going to be the same. The area is going to be bigger, but it's going to contain both of those. But it should have an aspect ratio of, we said, 3a over here for the height, and then for the length down here is 47b. All right, so far? So now I'm going to write that aspect ratio down, and I will just write it as the big one to the small one because that's the order I've been writing everything down in. So 47 over b, over 47 times b over 3 times a. And now remember that we have formulas for each one of these a's and the b's, so I'm going to substitute this stuff in, and I'd have 47 times b, and our b is the square root of a over 940, divided by our a value, which is, 3 times our a value, which is the square root of a over 12. What? Okay, I'm with you. And now notice that the top and the bottom have a in it. As a matter of fact, they have like the square root of a in it. So it has the same exact number. It would cancel each other out. Let me maybe cancel this thing in blue. So those two a's would cancel each other out. So the area is gone. All right, and then this would simplify to 47 times the square root of 1, because a is gone, 1 over 940, divided by 3 square root of 1 over 12. All right, that's not something you'd want to do by hand, of course, so we're just going to have to throw this thing into the calculator so we can get an approximate answer. So I'm going to start with the fraction formatter, and I had 47 on the top times the square root of 1 divided by 940. And on the bottom, I had 3 times the square root of 1 divided by 12. And now let's approximate this, and I get about 1.7701, blah, 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 blah. Okay, and now this is an irrational number. Irrational number means it cannot be written as a ratio of two numbers. And so what we're going to have to do is basically kind of approximate this number. Okay, so 1.7701. 2, blah, 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 blah. All right. It just so happens that that number is, it's not obvious from this work that we just did at all. That number is the geometric mean between the two aspect ratios. So this first aspect ratio, we're going to write this as just 4/3. You could write it as, say, 1.3 repeating if you wanted to. And now this one of 47 over 20, well, that one just reduces really nicely to 2.35, so we'll keep it at that one. We're going to find the geometric mean between those two numbers. So as we saw, as our definition for geometric mean, geometric mean is equal to, I have my first number, which was 4/3, over x is equal to x over, yeah, you can, go ahead. Oh, it's going to be a while. Okay, anyway, is equal to 2.35 to 1, whatever. Okay, and so now I'm going to cross multiply these two things. I'd get x squared is equal to 4/3 times 2.35. Or, I mean, remember that this 2.35, that was the same thing as 47 over 20. So I could write it like that if I wanted to. 4/3 times 47 over 20. And then the last step, just like we've done in so many of these exercises, take the square root. X is equal to the square root of 4/3 times 47 over 20. Well, that didn't look like what we had before. Well, here, let's just put it into the calculator. Let's put it into the calculator. Let's see what the heck's going on. So I have the square root of, let's put some fractions in here, 4 over 3. And then arrow out of this thing, and then times another fraction, and that was 47 over 20. And now let's approximate that to, oh, look at that. It's exactly the same number. It's exactly the same number. So this is also 1.77012. So here is a challenge problem for you. See if you can simplify this to make it look like that. So you can see that they are exactly equal to each other. So it's going to use, you're going to have to use some algebra and some arithmetic to show that those things are exactly the same. All right, so here's the deal. This is an irrational number. As a matter of fact, if I come back over here, if I just multiply the stuff that's inside here, I have these two fractions, 4 over 3, and then multiply that times the fraction 47 over 20. And this reduced fraction is 47 over 15. It's the square root of 47 over 15, which you're not going to get a whole number answer. You're not going to get a ratio of two integers. And that's why I'm saying these decimal numbers for this 1.7701 blah, blah, blah is never going to end and go on forever. Okay. So as far as like a television screen aspect ratio, that's not going to cut it. So what Kerns Powers came up with is the aspect ratio of the compromise one of, not ratio was 16 by 9. So 16 by 9, let's just put that into the calculator. So 16 divided by 9 and approximate this one. And we see that we get 1.777777 and repeating. And it's not exactly what we had before, but it's super, super close, right? And it's the compromise that takes into account a screen size that is going to magically and comfortably fit both the TV broadcasts of 4:3 with the widescreen of the CinemaScope, the widest of the widescreens. So that's a pretty fantastic and very interesting application of geometric mean. Okay, so that brings us to the end of this lesson about finding the missing side lengths in similar right triangles. We had two little methods here, and that was the heartbeat method, which said that the altitude, the third altitude drawn to the hypotenuse, was the geometric mean between the two smaller parts of the hypotenuse. And then we had the boomerang one, which is the leg length is equal to the geometric mean between the whole entire hypotenuse and the portion of the hypotenuse that's closest to it.